one cheat sheet,
Wait.
two sides, times 2 pages. Actually, does anyone know the time? I tried to look it up. 10:30. So Wednesday, May 11th, is that right? 10:30 to, I guess, 12:30. And what's the room number? Does anyone know? Is it the classroom or?
No, it's on the floor. It's not the classroom.
Okay, so the room is, we'll look it up. I tried to find it on NYU Albert, I just couldn't figure this out. Okay. All right. The basic 3 things, it'll be 1 problem from homework 7, then 1 from 1, okay, so 1.
Sandeep,
Yeah.
usually you give us 2 cheat sheets.
Yeah, that's what I meant, 2 sides and 2 cheat sheets.
Oh, okay.
Okay. Okay, 1 problem. From homework 7 to 9. Alright? So that's just, I think homework 7 is the one that nobody understood what was going on, so I'm going to just review that again. Okay, so let's just look at the homework 7 problem. Okay, so all the problems are the same. Basically, it's just you have the following. You have some symbols. Right?
What do you mean all the problems?
I mean, they're all the problems are using the same basic structure. All the problems in homework 7. They're all kind of having this basic diagram here. Right? There's a transmit filter, right? Or which is really just linear modulation, all right? And that creates the signal S of t, all right? And then you have S of t is the sum over n p. Okay, so that's basically linear modulation. Then that goes over a channel, g of t, all right? And then they do some, there's no noise in this problem. And then you have r of t. So this is step 1. Then r of t is g of t times s of t. So that's the channel. Okay, so it's 2. This is 1. All right. And then we have the receiver is really 2 parts. Right, and then here, it's basically okay. So what happens in the receiver is that there's a receive filter part, which takes this and multiplies by PRF of T, convolved with the receive channel, right? And then it samples R of n is equal to V of n t. Okay, so the only thing that's kind of important. All right. And then 2 facts that we proved. 2 facts. All right, 1, if PRX, so there are 3 conditions which are true, all right? So actually there's the first thing is orthonormal modulation. All right. If the following 3 conditions hold, if 1 PRX of PTX of T minus NT is a orthonormal set. All right. That means for different n, if I shift these, they're all orthogonal with one another. All right. 2, if R of t is S of t, i.e. there's no channel. All right. And 3, PRX of T is equal to PTX of star minus T, i.e. it's matched. Right? That's called a matched filter. If all of these three things are true, then R of n is equal to S of n. That means that this system, if you pick an orthonormal set and there's no channel, and you match it exactly, then you'll be able to recover the symbols. Alright? And so, if we had more time, it would have made you actually implement this. You actually knew in lab 5 or something, or 4, how to implement this part, and then we would have just added the channel. Yes.
So when it's not, we have that H of K, right?
Exactly.
I have a question, because in your slides, you write a big omega sign,
Yes.
or like the ohm sign. Is that what the same as just the small omega?
No, okay, that's a good question. Because, okay, let's write this. I'm going to write that. That's an excellent question. So, okay, when any of 1 to 3 do not hold, all right, this doesn't occur, all right? R of n is not equal to R of n is not equal to S of n, all right? In this case, you have R of n is equal to the sum over an impulse response. Right? In other words, it gets filtered in time. So let's say for an example here, all right, suppose that H0 is 0.9, right, and H1 is like let's say 1 or something, right? Well, let's just write it like this. Let's say 0.8, this is 0.15, and H2 is say 0.05. Let's just say it's an example, all right? This would mean that R of n is 0.8 times S of n plus 0.15 times S of n minus 1 plus 0.05 of S of n minus 2. Now what this means is that the signal, there's two impairments. Well, ideally we want R of n to equal S of n, but we see two impairments. One is that the signal that we want is attenuated or scaled, right? So there's two impairments. One is that there's a scaling on the desired symbol, right? That's really kind of like a channel gain. And then all of these terms are what are called inter-symbol interference. Or ISI. All right? And that comes from the fact that these are other symbols that kind of act as interference. You try to decode this, but you're really seeing effects from the other symbols, so it's kind of like noise. And the one and only one formula that you need to know is that, okay?
Coming back here, for the orthonormal modification.
Yeah.
Bullet point 2,
Yeah.
RT equals S of T, i.e. no channel. So when that equals that, it means that there's no channel.
I should say no channel impairment. That'd be better to say. Yeah, exactly. Because that means that this channel here, I'm getting exactly what I transmitted. The channel doesn't affect it at all. All right, yeah, no channel, but that's not right. Right. Now the thing is that, okay, so, yes. Okay. Now, you can also write, remember this, recall from the, did you guys do discrete time for your transform? Okay, so this means that, okay, so remember, now, there's a little recap, all right, on the DTFT, all right? If I have a sequence, all right?
Sandeep,
Yeah.
can I ask a question? So when you say Rn equals Sn,
Yes.
if you, like, is that equals to Sn plus Sn minus 1 plus Sn minus 2, or that would be only Sn?
Only Sn. So
Okay.
there's no inter-symbol interference. So you perfectly, whatever you transmit on symbol 10, it'll only show up on symbol 10.
Okay.
It won't show up on any other symbols.
Okay, and that's why we have there Sn minus 1, because we have interference.
Right, exactly.
Channel, okay.
So, yes. So this is just saying, I'm going to show you how to derive this. When 1 to 3 don't hold, more generally you'll end up with a channel where it's not a function of, I just gave an example. Instead of Rn is equal to Sn, Rn gets scaled, could get scaled by something. I didn't show how I derive this, it won't depend on the chapter. And then you'll have other terms from other delays. Does that make sense? Okay.
How about if we only have 0.8 Sn without Sn minus 1?
Then it would be considered also no ISI.
Okay.
That would be nice, because if that occurs, then you can always recover Rn back, Sn, by just dividing by 0.8.
Oh, okay.
Okay?
Okay.
Okay, so just let's do a recap of the DTFT a little bit. We all know the Fourier transform, but we did this a little bit, but it was all the way back in lecture 1, so let me just recap this. And to be honest, I'm not great at this either. So if we're given a discrete time sequence, say xn, all right, we can say x of omega as, I hope I'm getting this right, some xn e to the j omega n, all right? Oh, it should be a minus here, sorry. There should be a minus, all right? So that's called the discrete time. So this is slightly different than the Fourier transform, right? Because the Fourier transform with little omega, okay, we use, omega is kind of the digital frequency, digital angular frequency. All right, and that goes from 0 to 2 pi, all right, or minus pi to pi. It's periodic, or minus pi, or minus pi to pi, if you are. Right. In the Fourier transform, you have omega is 2 pi f, and f goes from minus infinity to infinity. Right. So that's the reason why they use this little omega. Does that answer your question? Okay.
Yeah.
I don't know if that sounds familiar to you from signals to systems. And there's an inverse for your DTFT, which is x of n, all right, is 1 over 2 pi, I hope I get this right, minus pi to pi times x of omega e to the j omega n d capital omega, with the ohm sign, right? And so you can get it like this. Now, we talked a little bit about how to do these. For the exam, I won't make you do anything unless it's like very, very simple. All right? Now, if you have this, can I erase this? Yeah. Okay. So there's only 2 formulas you need to know. I've almost summarized everything you need to know, and then we can just do some problems. All right? So if you have in general a sequence like R of n is the sum over h of k s of n minus k, then you can write in DTFT that R of omega is h of omega times s of omega. Does this sound familiar to, right? Or in other words, that h of omega is equal to R of omega over s of omega.